Hi folks, Mrs. Gates here. Today we are going to be looking at applying Newton's laws to systems that consist of more than one object. In this video, I will walk through several examples showing you how to work from what you know to what you want to know. To start with, let's review what happens when you exert a force on one object. Let's say we are exerting a 10 Newton force on a 5 kilogram cart. Assume that air resistance and friction between the cart and the ground is negligible. What will the acceleration of the cart be? To determine the acceleration of the cart, we will use Newton's second law, that the net force is equal to the mass times the acceleration. In this case, the net force is the 10 Newton push force. The mass is 5, and so dividing, we find that the acceleration of the cart is 2 meters per second squared. Now let's consider a two-body system in a very similar setup to what we just did. Let's assume that instead of having one 5 kilogram cart, we now have two carts, a 2 kilogram and a 3 kilogram cart. We are still applying a 10 Newton push force, but this time to the 2 Newton cart. Let's think about what the force and acceleration on the system as a whole would be, and then consider the force and acceleration on each cart individually. We will be drawing and labeling free body diagrams for each cart. Take a moment and pause the video. See if you can fill in all of the information on this slide. Use the chart on the left to calculate the acceleration and the net force on the system as a whole and on each of the carts. Then draw a free body diagram for the 2 kilogram and the 3 kilogram cart. You may or may not use all of the arrows that are shown here. Thinking through the relationships in a system like this is a little bit like solving a Sudoku puzzle. Every bit of information you get helps you find out some other bit of information. So let's start with what we know. Considering the system as a whole is exactly like what we did in our warm-up question. The net force is 10, the mass is 5, and so the acceleration will be 2 meters per second squared. Since both of the carts are moving along with the system, they will also have an acceleration of 2 meters per second squared. To find the net force on each cart, we simply say the net force is mass times acceleration. So for the 2 kilogram cart, 2 kilograms multiplied by 2 meters per second squared is 4 newtons. For the 3 kilogram cart, 3 kilograms multiplied by 2 meters per second is 6 newtons. Now that we know that information, let's start looking at the force diagrams. Let's consider the 2 kilogram cart first. We know the force of gravity will be the gravitational field strength, 9.8, or 10 multiplied by the mass. Here I used 10. So the force of gravity on our 2 kilogram cart is 20 newtons, and the normal force will balance that out and also be 20 newtons. We know the push force applied to this cart is 10 newtons, so we'll fill that in as well. Looking back to what we just calculated, we found that the net force on the 2 kilogram cart is going to be 4 newtons to the right. That means that there must be a force pushing back on the cart in order to balance out the 10 Newton force and give us a net force of 4 newtons. This force is a 6 Newton force, and it comes from a normal force exerted between the 2 and the 3 kilogram carts. Essentially, the 3 kilogram cart is exerting a 6 Newton force on the 2 kilogram cart. That gives us the net force of 4 newtons, and our 2 kilogram cart will accelerate along with the system. Now considering the 3 kilogram cart, we can fill in the force of gravity is 30, and the normal force will also be 30. Thinking about Newton's third law, since the 3 kilogram cart is exerting this 6 Newton normal force on the 2 kilogram cart, the reverse must also be true. The 2 kilogram cart is exerting a 6 Newton normal force on the 3 kilogram cart. So I'll fill that in on the arrow pointing to the right. Looking at the force diagram, we now have a net force of 6 newtons on our 3 kilogram cart. That's exactly what we calculated the net force on this cart should be in order for it to be accelerating at 2 meters per second squared. That means that this left-hand arrow doesn't represent an actual force. That makes sense since there is no friction or air resistance on the system. The next example we consider will be very similar. We still have a 2 kilogram and a 3 kilogram cart that are attached to one another, giving us a system that has a mass of 5 kilograms. We are still applying a 10 Newton force to the right, but this time we were pulling on the 3 kilogram cart with a force of tension. Analyze this system in the same way you did the last, filling in a chart of the acceleration and the net force, and then working to draw a force diagram for each of the two carts individually. As we solve for this system, we notice that the system as a whole will behave as the last two examples. The net force will be 10 newtons and the overall acceleration will be 2 meters per second squared. Each cart will also still be accelerating at 2 meters per second squared. That actually gives us the same net force on each cart as we had in the previous example. Let's look at the individual forces on the carts. On the force diagrams, nothing has changed about the forces of gravity or the normal forces. They will still be 20 newtons and 30 newtons respectively. The applied force, the pull force, is now applied to our green 3 kilogram cart, so we'll fill that in next, a 10 Newton force pulling to the right. Now we look at the net force on our 3 kilogram cart. The net force here needs to be 6 newtons to the right. That means that the left-hand force on that cart needs to balance out the 10 Newton force, giving us a net force of 6. That means we need a force of tension pulling to the left of 4 newtons. This force of tension is also pulling on our 2 kilogram cart. So we'll fill in a 4 Newton tension force on the 2 kilogram cart, but this time pulling to the right. These two forces are an equal and opposite pair according to Newton's third law. Now considering the 2 kilogram cart, the net force here needs to be 4 newtons in order to accelerate this cart at the proper rate. Looking at the forces we already have, the net force here is 4 newtons. That means that this arrow pointing to the left does not represent an actual force. Let's consider the same example again, but now let's add one confounding factor. Let's assume there is friction between the boxes and the floor. Here we are saying that the coefficient of the coefficient of kinetic friction between the boxes and the floor is 0.1. Recall that the equation for kinetic or sliding friction is that the force of friction is equal to the coefficient of friction multiplied by the normal force on the object. Pause the video here and consider the net force and acceleration on the system as a whole, as well as what the force diagram would look like for the system as a whole. Let's look at the free body diagram for the system first. We know that the mass is 5 kilograms. The force of gravity will be 9.8 or 10 multiplied by 5. I used 10 to give me a force of gravity of 50 newtons. The normal force on the system will balance that out. We know that the applied pull force is 10 newtons to the right. And next we calculate the force of friction, multiplying 0.1 by the normal force of 50 newtons to find that the force of friction pulling to the left on the system is a 5 Newton force. That means that as we find the net force on the system, we consider the 10 Newton force to the right and the 5 Newton force to the left, and we find that the net force on our system as a whole is 5 newtons to the right. Since the net force is mass times acceleration, and our mass is 5 kilograms, our acceleration will be 1 meter per second to the right. Now that we've considered the system as a whole, let's look at just the 2 kilogram box. Pause the video and take a second to consider the acceleration, the net force, and the free body diagram for this box. As we consider our 2-kilogram object, we know that its acceleration is going to be the same as the acceleration of the system, 1 meter per second to the right. That means that the net force, mass times acceleration, will be 2 newtons to the right. Now, starting to fill in our free body diagram, we will say the force of gravity is 10 times the mass, or 20 kilograms, and the normal force will balance that out. We can calculate the force of friction using the friction equation. 0.1 multiplied by the normal force of 20 to give us a 2 Newton friction force pointing to the left. Notice that we said our net force has to be 2 newtons to the right. That means the force of tension pulling to the right on the 2-kilogram box must be equal to 4 newtons. That means that there will also be a 4 Newton force of tension pulling to the left on the 3-kilogram box. We could have done this exact same analysis using the 3-kilogram box. We would have found the force of friction on the 3-kilogram box, used the pull force of 10 newtons to the right, and ended up finding a force of tension to the left of exactly 4 newtons. Hopefully this has been helpful in thinking about 2-object systems. Have a great day and happy physicsing.